Hello, Engineering 217. The big idea for this video is to look at models. So suppose I've got some object that's a perfect circle and I want to find its area. Well, we know just area equals pi times the radius squared. So we can get this area to as many digits of accuracy as we want because we can calculate pi to as many digits of accuracy as we want. So we're able to get or at least as exact as we want, a value for the area of this circle. Now in the real world, though, we don't have any perfect circles. If nothing else, atoms, the edges of objects are individual atoms, so it's not perfectly rounded on the edge. So what we might do is we might make a model for that. So a lot of engineering and science is about making models. These models are not intended to be exactly correct. The model that you choose as an engineer will depend on several things. Do you want something that's very accurate, or do you want something that's but maybe slower to calculate, or do you want something that's less accurate but faster to calculate? For example, what's the area of this car tire? Is it a circle? That would be, so can I just use maybe the area of that circle? Not bad. That might overdo it a little bit because it's flattened on the bottom. A slightly better model would be to maybe take that and subtract off this section down here. So we could figure out with some geometry how to get that area, subtract it off. An even better model would be to maybe consider these bumps in the tire. Okay, for example, let's go deeper and deeper and deeper into this calculation depending on how much accuracy we need. But keep in mind that you pay a penalty for making your model more accurate. The penalty, in my opinion, of losing sight of what you're really trying to do. So suppose someone in this case is trying to estimate the total mass of the car. For that person, I think just the circle for that, or modeling that tire as a circle, is plenty good enough. You'll get just really distracted if you start worrying about these little details of the edges of the tire. So I think you'll do a worse job overall because you'll spend so much time on the tire, you'll have no time left for the rest of the car. Okay, why am I giving this lecture now? Well, in strength of materials, we have a very common model that we're going to use. We're going to model the stress-strain relationship as a straight line. So we're going to take this stress-strain curve and pretend that this region, this linear region of the stress-strain curve, is exactly linear. It's not. It might be close, just like the tire was close to a circle, but it's not exactly right. So it's probably a better approximation when the strains are smaller. So this region down here would be the region where the approximation is really good. This region is where the approximation is decent. Here it's starting to get worse, and of course out here the approximation is terrible. So but even there it kind of gets you in the right order of magnitude. So it depends what you're looking for. But in our class we're going to be using this equation a lot, that the stress is equal to the slope of that line, which we call the elastic modulus, times the strain. And this thing right here is just very important for you to recognize that as just a model. Like other important models, like V equals IR is just a model. Like in physics 1, force equals the coefficient of friction times the normal force. There's our little mu. That's also just a model. So these are not exact equations. These are models that make our life easy. And note that all three of these models, we picked the simplest model we could. None of the variables have squares or cubes or square roots or anything else in there. Let me just add one more to this list. Here's another model, PV equals nRT from chemistry. That was also just a model. It's not exactly right, but at least in chemistry, you did it the favor of calling it the ideal gas law. You didn't call it the perfect gas law, the always correct gas law. You called it the ideal gas law. So we don't bother putting the word ideal on these equations. We just need you to know these are just models. They're not exactly right. They're sort of right some of the time. You just need to have a sense as an engineer when it matters to be more accurate. All right. So big idea, models. We use models. Bye.